All right, we're gonna watch it with sound later, but I just wanted you to watch it first with no sound because he gives away some of the details. So the first thing I want you to do is answer the question, what did you notice that was interesting in this video? If you remember last week, I had you write a summary. It's kind of the same thing. What happened in the video? What did you see? Was anything interesting to you? So answer that question now. What did you notice that was interesting during the video? And don't say nothing, please. What was happening in the video? You can just double click here and it should show up. So what did you notice? I noticed blah, 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 blah. Make sure on the one that says 9:15 on Tuesday, because that is today. And can you guys put your initials next to your sentence so I know whose is whose? All right. Take another minute. All right. So most people said he had a ball. He let go of it. It was attached to a string. It swung back and forth, but it never hit him in the face. Good. So now I want you guys to write a question. So what are you wondering about and what questions do you have? And just make sure they're science related. So I don't want any questions that are like, what university did he work at? What's this guy's name? Keep it about the science, keep it about the ball swinging. the motion, things like that. So everyone should be writing a question that they have now about the video. And then we're going to watch it with sound. So make sure you're writing it under the what are you wondering about and what questions do you have? We got some good questions. So someone said, is this potential or kinetic energy? Why didn't the ball hit him? Another, why didn't the ball hit him? Does the weight or the material that the ball is made of, I'm assuming, affects how this works? That's a good question. How do you find the mass and the velocity of the ball that was stuck? Good, those are really good questions. And hopefully, if not by the end of this week, next week, we will be able to answer all of those questions. Because next week, like I said, we're going to talk more about how to calculate the mass and the velocity. This week, we're going to talk about more of the different types of energy. So now, I'm hoping, will you guys let me know if you can hear this sound real quick?
I am such a strong believer.
Could you guys hear the sound? Okay, perfect. So all you have to do is watch right now. Pay attention to what he's saying. I know he has a little bit of an accent, but it's not awful.
Of the conservation of mechanical energy, that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it 0 speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0. Physics works and I'm still alive. See you Wednesday.
All right. I actually really had a professor in college who did that when I took physics. So now we're on, what do you already know about this video and how did you learn it? Did you already know about the different types of energy? Did you know about conservation? Did you know about the speed of the ball? So what do you already know and how did you learn it? Did you learn it in middle school? Did you do an activity? Someone in my last class said they actually saw this on social media before. What is something you already know? Good, so everyone, sorry, I'm just reading. So a lot of people had seen this before, which is good. So in the chat box, I want you to tell me your best guess or if you know. So when he was holding the ball at his chin, he kept saying that it needs 0 speed. He can't give it any speed. So that means he did not want to apply a force to it. What would have happened if he did push that ball or throw the ball or give it some type of force? And I want you to say why. Explain your answer a little. So he just dropped it and let it go. It went, came back, didn't hit him in the face. What would happen if he applied a force to it? What would happen and why do you think that would happen? Put it in the Zoom chat box. So what would have happened if he threw the ball? Put it in the Zoom chat box. So everyone's agreeing that it would have come back and hit him in the face. Why would it have hit him in the face? What changed from just dropping it to applying a force? What do you think would have changed? It's okay if you don't have the right answer right now, just put something. All right. So now we are going to look at a simulation. Let me make sure you can still see my screen. Can everyone see my screen still? Okay. So keep your thoughts about that in the back of your mind, because you'll have to answer that question during the independent assignment, adding what you learned during the independent assignment. Why would the ball have hit him in the face? So this is called conservation of energy. It's on Discovery Ed, and we call these explorations. You're like exploring a simulation. There's usually like worksheets and stuff that go with them, but we're not going to focus on that right now. We're just going to focus on looking at the graphs. So the introduction says, roller coasters are common in amusement parks, but they aren't just thrill rides. They are a great place to study the laws of physics at work. Explore the movement of a roller coaster cart along the tracks. As the cart moves, energy is converted from one form to another. Observe the relationship between these forms of energy and examine the conservation of energy in this adventure ride. And then you don't need to do that. So in the right corner, it says law of conservation of energy. It states that energy can neither be created nor destroyed, but it can change from one form to another. So that is like the textbook definition, or if you were to Google search the definition, but our goal is to be able to describe it in our own words. That makes us more likely to remember what it is. So we're going to watch a couple simulations on the track. So our starting velocity is 8 meters per second, and the mass of the car is 200 kilograms. When you see the graph after this goes, we're going to have kinetic energy, potential energy, and the total amount of energy. Oh, and also I'm not including friction in this simulation right now. We're in a frictionless world. Okay. So I'm sure that went as everyone expected. He went up and down, up and down. So at the bottom, let's take a look at this graph. So when he was at the very top, our kinetic energy was 0, pretty much. Our potential energy was very high, and it was almost equal to our total. So our total amount of energy was 50,000 joules of energy. And over time during the simulation, did the total energy stay the same or did it change? You can put it in the chat box. Wendy, I just explained that we're going to talk about the simulation. All right, So we have two people saying that the total energy, three people, that it was staying the same. It doesn't matter if we were at 0 seconds, 2 seconds, doesn't matter if we were down or up. The total amount of energy stayed the same at 50,000 joules of energy. So now I'm going to increase the velocity, how fast this cart is moving. And I want to see how that affects the energy. So I nearly doubled my velocity. It was at 8, now it's at 15. So before, my total amount of energy was about 50, where this red line was. Sorry, let me zoom in for you. So we know that the total amount of energy started with the red line at about 50. So what happened to the total? Did it increase or decrease? When we increase the speed, did the total amount of energy increase or increase? So the first, when I had the speed at 8, the energy was at 50,000 joules of energy. So the total was 50. When I nearly doubled the velocity, doubled the speed, the total amount of energy was no longer at 50. Did it increase or decrease the total? Did it go up or down? So when the velocity of the cart was 8 meters per second, the total amount of energy was 50,000 joules. So that was the first simulation. So now we increase the starting velocity to 15. So when the velocity of the cart was 15 meters per second, the total amount of energy was, let's look at this. So this is 50. What number is between 50 and 100? What number is between 50 and 100? Think of quarters. Yeah, 75. So when we increased the velocity to 15, the total amount of energy went up to 75,000 joules. So to summarize that, if the velocity of the cart is increased, the total amount of energy is also increased. I got all that just from this graph down here. So now I'm going to reset this. So remember, we started at 8 and we started at 200. Now I'm going to double the mass and we'll see how the total energy is affected. So now if we look at the graph, what is the total amount of energy? If you look at the graph in the bottom corner, what number does it start at? And it stays constant this whole time. How many joules of energy? 0, 100, or 200? What is the total amount of energy? 0, 100, or 200? Total energy is this purple line. Do any of these three lines go anywhere near 200? So the answer is 100,000 right here. So let me put this back. So if the mass of the cart is doubled, we went from 200, is it kilograms? Yeah, 200 kilograms to 400. The total amount of energy also doubled. Because remember, we started at 50,000 joules of energy. So I'm gonna go reset this and we are gonna look at the pie chart. So I'm just gonna let it play through once and just observe, look at how the pie chart is gonna change. All right, so this guy here is starting at the top. When he is high off the ground, does he have more potential energy or more kinetic energy? When he is high off the ground, he has a large height. Does he have more potential energy or more kinetic energy? Good. When the cart is high off the ground, there is a lot of potential energy. That was just me summarizing it. So now, when the cart is low to the ground, there is less potential energy. So I'm going to continue this. Are you able to see the mouse on my screen? Like how I'm moving my cursor? Okay. So I want you to watch specifically from when the cart goes from the top down to the bottom and back up. And I want you to be able to describe the cart's motion. Is it going to be speeding up or is it going to be slowing down? So I'll play it again. Right at the bottom, whoop, whoop. Is the cart speeding up or slowing down? Chris says speeding up. Who agrees? Who disagrees? Wendy agrees. Derek agrees. When it's dropping, good. It's speeding up. So when we are dropping and speeding up, what type of energy is increasing? So watch the pie chart this time. What color are you seeing more of? So we're seeing more blue and we see more blue. I'll show it again. When the cart goes down, the amount of kinetic energy, or the blue, is increasing. So at this top, we have more red. At the bottom, we have more blue. So that's telling me that when speed or velocity, however you want to say it, the velocity is increasing, the kinetic energy is also increasing. Because as he goes down, he gets faster. As he goes down, the blue part of the graph got bigger. So we figured out all of this literally from just watching colors change. We didn't have to do any math. We didn't have to make any graphs. All we had to do was observe. So you can get a lot of information by literally just watching. So let's all go back to the Teams page, the collaboration space. And I'm going to insert a picture. And I like to call him man standing sideways. All right. So I am going to use the draw function at the top here. And I'm going to draw the balls. Wow, that was an awful line. I'm going to draw the ball in 3 different spots. That looks like how the ball swung. So the ball started right here at his face. It swung down. And then it went back up. Does everyone remember seeing these 3 spots? Started near his face, swung down to the floor, and came back up. Yes? Does everyone remember seeing that? All right, we have 1 yes. So we're going to describe the 3 different types of energy that we looked at during the simulation. So we have, let me try to use the same colors. So we had the total energy. So what do we know about the total energy? I'll label these point A, point B, and point C. Does the total energy change or is it constant? Think about the word conservation. Does the total amount of energy change or does it stay constant? Let me go back to the simulation. Did the total energy ever change during one single ride? I understand what you're saying. It changed from 50 to 100. But during this one path, when the car was going 8 meters per second at 400 kilograms, did this total energy change during that ride? Good. So we saw that it was a straight line on the graph. Our total energy, if we're not changing anything, just remains constant. So because we're not changing the mass of this ball from A, B to C, and we're not changing the speed, the total amount of energy is constant. Wow, this is hard today. So there's two things that make up the total energy. Something plus something else. What do you think those two things are that make up the total amount of energy? If you think about it on this graph, what two things made up the total? Good. So to find the total, we just have to add together potential energy and kinetic energy. So now I want to talk about potential energy, PE. So on the simulation, we discussed that when he was really high up on the roller coaster, he had a lot of potential energy. Think about the pie chart. At the tip top, he had a lot of potential energy. So looking at this model, where do you think there's the most potential energy? Where is the top for this ball? Sorry, I don't know why this moved. Oh my God. So Wendy says A and C. Which one is a little higher? A or C? It's supposed to be A. I know my drawing skills are not that bad. So the starting high point when it's at his face, this is where we will see the maximum potential energy. And I'm going to write a summary sentence. So point A has the most potential energy because it is where the ball is the highest off the ground. Plain and simple. The ball is the highest off the ground at point A, so that means it's going to have the most potential energy there. Now I want to talk about kinetic energy. Where do you think we have the maximum kinetic energy? So we can figure that out two ways. Remember, kinetic energy means it's going to be low to the ground and it's going to be going the fastest. So Wendy says B. We got another B. So B is the spot on this diagram where there's the maximum kinetic energy. And I have two ways that I can explain that. So point B has the most kinetic energy because it is where the ball is the lowest to the ground and it has the greatest velocity. So that's where it's going the fastest. All right. So I know I threw a lot at you today, but that's okay because your independent assignment is going to go over the total energy, what potential energy is, what kinetic energy is, and looking at a couple models. So there's one last thing to do today, and it's kind of like what we did last week. So we are going to create a hypothesis. Remember, that's like a guess that answers the question that we're trying to answer. So I know that, like I said earlier, you saw the textbook definition for the law of conservation of energy, but I want you to put it in your own words. So below this section right here, I want you to put in your own words, what is the law of conservation of energy to you, and what are some examples of it? It's okay if it's wrong. It's okay if it's incomplete, because you're going to add to it after the independent assignment. So before you can leave the meeting today, you need to write a hypothesis, a guess. The law of conservation of energy is blah, blah, blah. Or the law of conservation of energy can be described as however you want to describe it. Those are just two examples of how you could start your sentence. So before you leave class today, you need to write a hypothesis, which is just a guess that answers the driving question, what is the law of conservation of energy, and what are some examples of it? You can write it right below my sentence starters. And make sure that you guys put your initials after so I can see whose is whose. Think about what the word conservation or conserved means. It means to stay the same. So how is that describing the energy? Remember, I want it in your own words. I don't want the Wikipedia answer. So remember that each week you have an independent assignment and they're all posted on Teams under assignments right here. So I already put this week's up. I put it up yesterday so you can get started on it. Even though these will say that they're late, if you're missing one, you can always make it up. There's no late penalties during early start. Let me go back to the collaboration space. So if you have wrote your hypothesis, if you wrote down your guess, you are free to leave the meeting. You need to do this hypothesis because you won't be able to finish your independent assignment without it. So just take a guess. There's no wrong answers right now. What does conservation of energy mean? Is it changing or staying the same? So if you wrote your hypothesis, you are free to leave the meeting. Thank you for joining. Bye, Anya. Bye, Clark. So remember, it doesn't have to be complete. You can always come back to add to it. Bye. Bye, Wendy. Bye. Is energy staying constant or is energy changing? All right, Derek, I'm going to end the meeting, but the collaboration space is always open, okay? So take your time. You can always come back to it, okay?